So in this rather short lecture, I'm just going to briefly look at some of the definitions and units, some of the terms that we'll be using in to describe the magnetic properties of materials. Okay, so we've seen that it's going to be the magnetic moments of the atoms, for example, in a material that gives rise to its magnetic behavior. So the magnetic moment, the small m, let's see, so that's the magnetic moment, small m here, that we defined earlier as m being equal to I times A, okay, where A is the cross-sectional area. So if you like, the units of little m, the units of m would be amps meters squared. Okay. Now that's a sort of microscopic quantity. Often we want to refer to more a macroscopic property, so a property of a body. And so in this case, it's useful to introduce the magnetization. So this is capital M. And the magnetization is about the volume density of these magnetic moments, whether they're permanent magnetic moments or they're induced magnetic moments. Okay, so they're quite straightforwardly related. We just need to multiply up by the number density. Okay, so what about the units of so the units of capital M? Okay, well, this will be the units of little m, amps per meter squared, and we'd need to divide by the units of, multiply by the units of n, which is 1 over volume, so this would be meters to the 3. So the units will be amps meters to the -1. Okay, so that's what the units of large M will be. Okay. Now, if we have our sample that is magnetized, it has a magnetization capital M, this will in turn create a magnetic induction field B that we would measure in Teslas being the SI unit, and that's straightforwardly represented here. They're proportional to each other just by this constant mu naught. Okay. So we want to think about magnetic materials in an external field. It's often useful for us to introduce the magnetic field strength H. Okay. So we can either use B or H to discuss magnetic fields. So H has units of amps per meter. Interestingly, that's the same as magnetization. Okay, and it's called various things: magnetic field intensity, magnetic field strength, magnetic field, magnetizing field. Okay. The field B has units Tesla or Webers per meter. Weber being the unit of magnetic flux, and hence it's called things like magnetic flux density, magnetic induction, and magnetic field. These names are all incredibly confusing because, as you see, both B and H can be called the magnetic field. Now, my own preference and what is to use something that is unambiguous. So I tend to say we apply a B field or we apply a H field. Okay, and I often call both of them magnetic field, or a magnetic field H or a magnetic field B. So I normally refer to them by their letter, so everyone is clear about which of the two that I'm talking about. Okay, I think relying on one of these particular names and for everyone to agree on what that name is unrealistic. Okay, so my suggested practice is to always include the letter. You can always, if you're reading something and they say a magnetic field of 4 Tesla, well, that must be B because they're giving you the units. Okay, so checking the units is a way because B and H do have different units. Okay. In a vacuum, there's a simple relationship between B and H. B is just mu naught H. And you can see from this is a similar relationship between B and M. So B was equal to mu naught M in a magnetic material, and that's why B and H have the same unit. Okay. Now let me just introduce a notation, something that is perhaps not universal, that it's sometimes helpful to call the magnetic field in the vacuum B naught. Okay, so we're often going to be thinking of a piece of magnetic material or a piece of non-magnetic material, diamond or something, and we're going to look at its response to an external magnetic field. Okay, and so we'll often think about that external magnetic field, the magnetic field that we apply, as B naught. Okay, and B naught and H, because that's in the vacuum, they're simply related to each other. However, inside the material, the local B field is going to be different, either because there's a permanent set of magnetic moments in the material, or because there's some induced magnetism in the material. Okay, so the B field at any point inside the material is B naught, the applied field, plus some induced field. Okay, and that induced field is coming from these magnetic dipoles. Okay, so we can write. So this is that statement that I've just said, that the actual field at any point inside a magnetic field is the applied field B naught plus the induced field. And we know from what we saw earlier that the induced field can be written in terms of the magnetization. Okay, so this is simply the local field is the externally applied field plus the response of the material. Now, there are two different quantities that we might use to characterize the magnetic response. For non-permanent magnets, often the most useful is the susceptibility. Okay, so the susceptibility is dimensionless, and it's just a proportionality constant. Okay, it's proportionality between the applied field and the response of the material. Okay, so here I've written it in terms of H. So H is what is applied, and M is the response. Okay, so the larger chi is, the larger the magnetization of the material for a given applied field. It's sometimes useful to write that in terms of B naught, the applied field, and to do that we just have to put this extra universal constant in, mu naught. Okay, so that's an equation that defines what the susceptibility is, chi. Now, I will say that when you go on and do the electrical and optical properties, you'll discover there's another term called the susceptibility that relates to electric fields and the polarization of materials. Now, in this course, when I write chi, I always mean the magnetic susceptibility. Okay, and in fact, I'll just call it the susceptibility, and I won't generally preface it with the word magnetic. But in this course, you should understand that this is always the magnetic susceptibility. If we were in a scenario that we were mixing the two together, for example, we were in some sort of magnetoelectric material, then we might need to be more precise, and we might need to very carefully define a symbol for the magnetic susceptibility and one for the electric susceptibility. But for the moment, everything in this course is magnetic susceptibility. Okay. Now, for non-magnetic materials, so not permanent magnets like iron, the susceptibility is normally extremely small, the order of 10 to the minus 5, could be 10 to the minus 7. What that's telling you is that the response of a normal material to an external magnetic field is very small. Okay, so the kind of magnetic fields that are generated, these induced magnetic fields, are 5, 6 orders of magnitude smaller than the magnetic field you've applied. Okay, so chi is an extremely small number. We can also define the permeability. Okay, and there's a wordy definition of that down here. So the susceptibility is the permeability is trivially related to the susceptibility. It's just 1 plus the susceptibility. Okay. And so the susceptibility, you see how easy it is to get the words mixed up. It's much easier, I find, when I'm writing symbols down. Okay, if we look down here, whereas chi was the relationship between H and M, mu of r is the relationship between the, if you like, the applied field B and the actual field within the material. Okay. So, initially we'd started with the local field being the applied field here and the magnetic response of the material. Okay, and they're quite trivially related. Now, for typical diamagnetic or paramagnetic materials, as I said, the susceptibility chi is the order of 10 to the minus 5, 10 to the minus 6. That means mu r is approximately 1. So for non-magnetic materials, mu r is not the most useful quantity to talk about, because I'd have to store it to a good number of decimal places to capture the fact that it's different from 1. When is mu r particularly useful? When we're dealing with permanent magnets. In those cases, the susceptibility can be thousands, tens of thousands, hundreds of thousands, and mu r then can be appreciably different from 1. So mu r is a useful parameter for permanent magnets, and the susceptibility chi is most useful for non-permanent magnets. Okay.